joint consulting, where I finally headed up the AI and ML team and PwC's Johannesburg actuarial practice. For 4 years there, consulting to companies and banks on the implementation of AI and machine learning. And then took this role as head of data science at the JD Group about 15 months ago. And basically my brief, what management told me, to listen, be very excited. We've heard about all these machine learning advancements and so on. We're still a bit skeptical because we had some POCs, did some POCs here, consultants in India some time ago, and didn't really get any results in our credit models in terms of superior predictions. But we've got a cloud strategy, AWS, and we're migrating our data lake to cloud. So we want you to show us what this technology can be done and tackle our credit area. So I set then out to start with the credit model space. So we're going to talk a bit about, just want to set the scene a bit about traditional credit scoring models. So you guys have a feel of what a sort of context is. And then I would like to share our journey where we went through, started applying advanced machine learning approaches, credit machine learning algorithm excellence, getting the best fit for purpose type algorithms is the first step that we objective we set. And then once we achieve that, we said, okay, are we going to now do robust inference, reliable predictions at low cost deployments, and then the whole MLOps space of continuous deployment, continuous retraining of models, etc. So been an exciting journey. At 15 months, I started building a team, and we set out to do quite a few objectives for us. Okay, so just a couple of points on traditional credit scoring models. Well, this is a fairly mature space. I mean, credit decisioning, automated credit decisioning started about 20 years ago. Like say, Fair Isaacs in the US started building scorecards. It is quite sophisticated. There are many models running in sort of in a lending environment. And it's fully automated. Yeah, I'm talking about a consumer credit space. So these are high flow value, high volume type credit loans, pretty high risk. If you get it wrong, there's the losses can be quite high. If you get it right, the profitability can be quite good because the margins is quite substantial. And if you look at across the space, I mean, logistic regression is still the go-to modeling technique. Even with its limitations, which has been somewhat been overcome by some rudimentary feature engineering that credit scorecard builders started to do. But despite the benefits of AI and machine learning in this space, there's not really been a wide adoption. That's been my experience in the consulting space where I work. And that's could be attributable to a couple of factors. I mean, the GLM methods like logistic regression, obviously, very simple methods and very interpretable, which is very important in the credit space because always the issue of bias, and you got to explain to borrowers why did you decline their application. And what scorecard builders started to do, they started to combine some simple feature engineering techniques, as I said, optimized binning, nonlinear transformation of the data with logistic regression, and that actually gave it quite a lift. And so it turned out that many times I start looking at, get excited about machine learning algorithms and tree-based algorithms that don't really see that significant benefit. Maybe 2 to 3% accuracy improvement, but certainly not enough to make a huge investment and a huge transformation to technology. Of course, open source is the issue. Many of these lenders and banks don't have open source policies. They're very limited Python skills. I mean, as we all know, this is primarily a SaaS-based environment with a lot of SaaS software being used and a lot of the SaaS tools, which are quite established and mature. And of course, then you still have limited number of variables here, because primarily in South Africa situation is still, 80-90% of the lending is still based off bureau data, and all the variables are important. So the so-called alternative data space using non-bureau data is still very limited, although it's growing. And of course, it's a regulated environment. So it turns out that a lot of these credit providers are not really that excited about the space. So I set myself a personal objective. I wanted to prove to myself and management that this technology is real and it can work and it can give the benefits that we all thought it could. Okay, so the first phase of this was to start looking at our machine learning platform blueprint. It was very important for us not to build Python, get started on Google Colab Pro Plus with a nice GPU at low cost, and you can build some very fancy models very quickly, but then you can't deploy them, you can't, using and consuming the models, you can't scale, et cetera, et cetera. So we decided to, and we had to, basically, as a requirement strategy of a company, was AWS data lake strategy, which we had to integrate with. So on the left side, we got Amazon EMR, PySpark for data engineering, and the S3 file management system as the data platform. And we then started to define our blueprint of our platform for the future, build around the SageMaker, AWS SageMaker ecosystem, which is quite sophisticated and quite advanced. So a couple of key points. I mean, the first thing for us is what we call fit for purpose ingestion. I mean, data is everything here. You want to have reusability of features. You don't want to go through all the effort every time with the same feature in a different model. There's masses of data. Yeah, we also have streaming data for our e-commerce platform, etc. You want to be very specific on just those features that's going to add value. So the first key component for us we started implementing was the feature store. We've got online and offline feature store. Then the algorithm, what we call algorithm excellence, is our fit for purpose, getting the best in class algorithms of what we try to do. So that's the whole orchestration, experimental orchestration pipeline tool set that we started to put in place there. And from then on, it's ML ops, is to take from those experiments, once we've got the best experiment and candidate model, to take it through the code commit, code build, and code deployment in an automated pipeline. Then serving then our model registry, sort of at the center of this, register our models there, train and serve and predict. And then continuous deployment through automated monitoring, triggering of threshold alerts for retraining requirements, and then kicking off automated retraining pipeline. So those are the key elements of our blueprint and architecture around the SageMaker environment. Of course, we integrate a lot of open source elements there, but SageMaker has some of AWS's own algorithms, but of course, can integrate all the open source TensorFlow, PyTorch, scikit-learn libraries, etc. So we have everything in that environment that we need. Okay, so algorithm excellence, what do we mean by that? Well, first of all, that's about finding the best fit for purpose algorithms for the problem domain, credit in this case. And what we also want to do there is to say we want to standardize. We don't want to go every time, every credit model requirement comes up, can reinvent the wheel again and go and do research and try many different algorithms. We do it once off and evaluate a large number of algorithms and combination of algorithms, and then we standardize and we define the algorithm set for the problem space here, and then we stick to that. And then in a year's time, we're going to review and revisit and see what's happened out there in the market in terms of algorithm developments, and then add new ones to that and take ones away and so on. But that way we can save ourselves a lot more time. We'll be a lot more agile, and we can deliver a lot faster. So the first thing we try to do is say, well, okay, let's have a look at the second generation gradient boosted tree algorithms, non-scikit-learn ones. As you know, the first generation of likes of XGBoost and Rana Forest, about 10 to many years old already, so there's been a new generation of these algorithms quite recently. And we evaluated that because tree-based algorithms are still the best for tabular binary classification problems, and if we could get a good lift here, then obviously we can just standardize on these. So we had a look at this cat boost. We evaluated cat boost. I'm not sure if you guys know it. It's a Yandex. It's a Russian internet company. What cat boost does, it automatically encode categorical variables, so you don't have to do any categorical variable encoding. It uses a target encoding method, and it's done in such a way that there's no target leakage. But we didn't, got some good results, but not consistent. Some data sets will work well, some not. And then, of course, it's not so scalable, GPU support limited, and then it's not really open source. It started off pretty, looking pretty excited, but sort of open source participation has died out a bit. Like GBM, the Microsoft one, we're quite impressed with Light GBM, very scalable, awesome robustness, consistent every time on every model. We start out in every credit data set, it would give reliable, top, good performance, super fast, scalable, multiple GPU support, and so forth. And then XBM, explainable boosting machine, is also Microsoft invention. It's a full interpretable algorithm. It creates outputs, weights, and coefficients that's similar to logistic regression. A little bit robustness, reliability, a little bit of issue, and then compromising in accuracy. Interpretability is very important in credit models. But this XBM doesn't use a post hoc type of interpretability calculation afterwards. So that is actually more accurate in interpretability, but we just felt that the accuracy compromise is too large. Okay, so out of these, what did come out, we liked LGBM, and we decided to use it as our baseline. So going forward, whatever we do, we will try the GBM algorithm, and we know what we can achieve, and then start improving from that baseline in terms of its performance. Type transformers, I think if everybody knows about transformers now, it started off with Google NLP transformers, BERT, and these algorithms came out, I think, 2018 or 2019, and then now everything is transformers. You have convolutional neural net transformers, time series transformers, and then also tabular data transformers for classification problems and regression problems, which came out, I think, about 2 years ago. As you know, transformers basically embed the categorical variables, which have to identify an input layer, and then it transforms that into contextual embeddings using those attention mechanism, which can lead to pretty good accuracy. And then after those transformations been done, it's then combined with the continuous features and then trained as a neural net, minimizing the loss function. So very, very powerful, and these architectures are just becoming more sophisticated and growing and getting more and more powerful. So our assessment of type transformers was very, very exciting. I mean, if you looked at the whole credit scoring space, vanilla neural net transformer neural nets were never really even considered. They would not feature. I mean, up to 2 years ago, or when we had these DNN classifiers, we were tried as a candidate in the credit model. The performance was so poor that it was actually kind of very disappointing, and the main reason being that neural nets before transformers didn't really have the ability to deal very effectively with heterogeneous data. They work very well on homogeneous data like pixels and tags, but these credit scoring space, you got heterogeneous data, integer, float, categorical, etc. So Google released TabNet 2 years ago, and the TensorFlow, we didn't like the TensorFlow implementation so much. I mean, the PyTorch was a lot more efficient, but now you got quite a few TabNet transformers. the likes of Fast AI has actually got a good algorithm that we like. And then, of course, AWS Labs also released theirs not too long ago. There's a little bit different nuances under the hood, which we actually quite like. The performance we find of these tabular transformers, of course, the more categorical variables you have in your data set, and also you get better performance. If you have few labels in a data set, you also get good performance, and also when you have large missing values. However, the categorical data percentage in our data sets are typically not that large. It's mainly continuous variables, continuous data, although this is likely to change forward, going forward as we bring in more non-zero data, which is the plan in the future. So bottom line is that tab transformers did not improve on GBT. They just sort of from way underperforming the GBTs in the credit problem space. It caught up, and it's, you know, sort of sitting there as one of the top 2-3 best performers, but not to such an extent that we would drop everything else and say, okay, yeah, we're going to get a significant lift compared to something like a light GBM on a consistent basis. Okay, so we have to continue our search. The next space we started looking at was what is also becoming like a popular technique is you integrate hyperparameter optimization across the feature engineering space and the traditional prediction algorithm hyperparameter optimization space. So it requires sort of a feature engineering heavy approach, where you look at many different feature engineering techniques and also algorithms that you use in feature engineering, like unsupervised algorithms for segmentation and dimensionality reduction, etc. And then what the approach is then to actually, for those feature engineering techniques and methods you select to optimize their parameters combined concurrently with a prediction algorithm hyperparameters. And every experiment has got a different combination of feature engineering techniques with their parameters and a different prediction algorithm with its hyperparameters, and then large number of experiments, you try and get a most optimal method. Now, it's surprising what good performance you can get with this approach. Sometimes with a very simple algorithm. In many cases, I've seen a linear algorithm perform exceptionally well and outperforming a lot of other things, was combined with some many different feature engineering techniques that you optimize at the same time. The problem, though, is the whole feature engineering automation is not a mature space. There's a lot of manual effort involved. I mean, each and every case you have to look at many different combinations of feature engineering techniques, and it's becoming too time-consuming and just costly for the benefit you can get. But it can be quite an efficient, quite a powerful approach if you have the right level of automation behind it. Okay, and then the last option we evaluated was stacked ensembles. Okay, stacked ensembles, you all know, it's been around for some time, and particularly sort of popular application of this is just use tree-based in the stack ensemble architecture. We started over that, but again, not really getting exciting benefits, and then we decided to go for a more complex type stack ensemble, where have up to 3 stacking layers, and then typically 10 to 15 base learners, and those base learners algorithms can then basically be anything. Typically, what we end up with is neural net, including the tab transformer. Then also becomes a base learner combined with tree-based algorithms. Kernel-based can also work in some cases, but and GLM algorithms. But typically, the tree-based algorithms, most of the popular ones, combined with the tab transformers, and also some vanilla neural nets in there, in a 3-layer stacking where you have the base learners, then combine them into up to 3 layers. And then the super learners, the stacked layer, were then learned from both the base learners' predictions as well as the data. So they get trained on both the data set, the features, as well as the predictions of the base learners. Okay, our approach in this, and again, there are many approaches here, but we follow FE light approach, feature engineering light. We don't do a lot of feature engineering, so no variable selection, no dimensionality reduction, no multi-collinearity thresholds and dropping of features because of that, no treatment of outliers. We basically let the power of his algorithms do all the work. There's some tweaking we do at the end. I'll get to that a bit later. So we do the basic and just missing data treatment, imputation. We do some categorical encoding because some of these algorithms don't do that automatically. Some of them will. So we identify the categorical variables in the input. But not too heavy. And then text features, we do text featureization through n-grams. But that's about all. There's about 4 or 5 feature engineering steps we go through. And then also no hyperparameter optimization. Okay, there's a debate whether you still want to do hyperparameter optimization. I mean, the research that we've seen, if we haven't tested it out, is that the lift you get through the power of abstract ensembles is not, you're not going to get any major additional, significant additional benefit by doing hyperparameter on top of that. And at the same time, we add a large amount of complexity and cost. So we stuck to no HPO at this stage. And then we start to apply this on all our data sets and large data sets, small data sets, once with much better data, much more labels, ones with fewer labels, etc., and so on, what you find in the credit space. And we started to meet our target of about 12% plus accuracy improvement. And we could do that consistently. Each and every data set and model we tackled, we right from the word go started to see some excellent results. So we're very excited, and that was exactly what we were looking for. And we decided to then standardize on all these on stack ensembles. And we're then faced with how are we going to deploy this at low cost and without overfitting and to give robust, consistent results. Okay, so then we started our evaluation and said, well, okay, these let's now also look at the prediction time, the latent and prediction latency. Compare and plot that against the performance of these various stack ensemble models, and then see what that picture looks like. And it sort of gets to this kind of picture where you have the single algorithms like a neural net tabular from fast AI and so on. We get very low, very good inference latencies, couple of seconds. But as soon as you start moving to the ensemble, the stacked ensemble, level 2, level 3, or whatever, you get better performance, obviously, but massive. It could be up to 20 times easily longer prediction time. And obviously, the more complex the stack ensemble architecture is, that just aggravates and make it longer prediction time. So it's become a challenge. The problem is that training is sporadic, and on cloud you can go and do so-called spot instances where you give it lower priority, and then you can drop the cost of the training 60-70% because of the lower priority. But when you go and spin up a compute engine on cloud to do the predictions, it's going to stand there for 24 hours a day, a lot of time not being utilized. But when it is used, it's got to give good prediction performance latency. And yeah, that could run out of cost very quickly. Okay, so we were then faced with this problem and realized, well, we're going to have to do something. We're going to have to simplify the model, the stack ensemble architecture, because that could be very, very complex. Many different models have been combined there. And we have to do that to really, for two reasons, is to reduce inferencing costs, as I said, but also to reduce potential overfitting. We are using various indicators to signs of overfitting, divergence between train and validation and out of and hold out test performance and so forth. But the risk of overfitting is always a potential. The potential and risk is always. So we have to address that. The interesting point is AWS has done a lot of studies in this space. Their finding is that inferencing cost, so the post-deployment prediction cost, is typically 90% of the total cost of ownership of a machine learning model. So that is a huge cost. Obviously, we had to find a solution without reducing the model accuracy significantly, then else all the hard work would have been undone. And then we looked around various alternatives and then decided on a model distillation technique or approach of using a teacher and student method. What happens here is that you train the complex model, the teacher model, which is a stack ensemble in this case, and it makes predictions on a large data set with many rows. And then you train a simple, very simple model, typically a single algorithm on that large data set on those predictions. And it can learn from repetition because it just can very quickly pick up the pattern between the features and the ranges of values in those features and the outcome because of the many samples and labels it has in that data set. And it turns out then that the student model can then perform as good as the teacher model, and the student model is then deployed with a lot lower inference costs and reduce overfitting risk. Okay, so our challenge was then, well, where do we find a large data set with many rows that this teacher can predict on for the student train? Obviously, we didn't have that, so we turned to HDD, synthetic data or SDG, sorry, not HDD, synthetic data generation algorithm to address that issue. So the model data distillation process works as follows. You typically get a source data set. Your normal data set, you build a model of, you split that into all that set, and then a training validation set. And then we train a teacher model here on the left, the stack ensemble. And then the teacher model, we then take the training data, the training features of the training set, and we apply an SGD, synthetic data generation algorithm to that to generate synthetic features to mirror those distributions we found in the training set. We typically, that's about 2 to 5 times the data augmentation increase the rows in the training data set by about 2 to 5 times, typically up to 100,000. Up to 100,000, we're okay. And then we end up with an augmented training data set just with the features that we've now augmented. And then the stack ensemble, a teacher model, we use then to predict on those features to create the target column. Okay, so then we have a full data set with features and target, which we then split into training validation again, and then use the student model, single algorithm to train on that, and then we evaluate that on the original whole data set. So that's the process. We've done on the data set, and the challenge we had here, typically, this was a very small data set, so what we found in this data set is that the student actually marginally outperformed the teacher because of the significant number of much larger data, many rows it was trained on. Here we started off with about 6,700 rows in a training set, which was augmented to about 37,000, which the student then was trained on. And then so far, what we've seen post-deployment, we've also seen the student model is actually more robust. It's more reliable on new ground truth data coming in, obviously because it's trained on a much larger data set than what the teacher was trained on. Okay, so data augmentation or synthetic data generation is a large space on its own, and there's some very complex algorithms. We started looking at that, and of course, GANs, also variational autoencoders could be used there, but GANs is the go-to method. You know, some very good algorithms out there, TGAN or tabular GAN, I think it was invented at MIT. For synthetic data generation, they perform quite well. However, we came across this Munch algorithm, M-U-N-G-E. I'm not actually sure what it stands for, and it's been around, and it's actually exceptionally simple algorithm. It's you can some good examples on GitHub. You can go and read up with it. It samples directly from a non-parametric estimate of a joint distribution. So it doesn't use, I'm not sure exactly what techniques it uses under the hood, sort of traditional statistical, tweaked statistical methods, but it's exceptionally simple and super fast. And the beauty, of course, of this, synthetic data generation is very easy to test. The distributions you generate, you can then compare to the original data set, looking at the statistical means or KL divergence or any of these type of metrics, and you can very quickly see, if it's performing well or not. So that worked quite well for us. Okay, so we addressed that problem, and then we were hit with, now we can build powerful models. We can also address the inference issue and cheap, low-cost predictions. But how are we going to fit this lot into our IT architecture, which can be a stumbling block for many machine learning implementations, because you have to go through a lot of IT standards, etc., etc. And in our environment, we defined a architecture like this. We've got on AWS SageMaker, our data machine learning platform, model governance, and whole ecosystem I described earlier. And then we integrate with the AWS tools into various front-end applications that will use our modeling services at the back end. And luckily, we could use the AWS integration tools, the very powerful microservices, API gateway, event bridge, event bus type tools, and that effectively enabled us to bridge that integration gap into the enterprise solutions using these AWS tools. Our credit models being implemented uses real-time consumption by APIs. So we use SAS ID is a SAS decisioning front end, which collects all the data from the bureaus. The application is captured in there from various sources, mobile, internet, branch, etc. And it then passes the scoring request for a prediction via REST API through the API gateway, which is authenticated there. That passes it on to a Lambda event handler. The Lambda would route it to the type of model that's going to be used there. There's several models, and then deploy on AWS SageMaker, do the prediction, and pass the result back all the way back. Now, we're using these microservices APIs. We're using Docker containers to package the models. And then there's Lambdas, all event, asynchronous event handling, for fast 24-hour response. What we also managed to achieve is to deploy these models as serverless on the AWS hosting service. Serverless endpoints is a new feature in AWS. It means you don't have to spin up or reserve any compute resource. If the model prediction takes 2 seconds, you get charged for 2 seconds. So a very low cost implementation we managed to achieve there. Okay, so automated monitoring workflow is still not fully in place yet. But so far everything looks good. What we do there, we do real-time data drift capturing, so all the predictions coming into the endpoint from the front ends, the input, the features that's used in a call, in a request, as well as the prediction output is then stored and captured, and then we've got a data drift monitoring there that on a 24-hour basis then would detect issues in the data, sufficient data. It will start, also do the covariate shift calculations for us, etc. Violations that is also put in the S3 bucket. And then the ground truth data, once we have sufficient outcome data available every couple of months, that's then merged back to the predictions that we've tracked here. And there we do various comparisons and metrics of concept drift and the feature importance drift. And then we use the CloudWatch environment for all our thresholds and alert settings to alert us when there are problems in the models and they need to be retrained or data needs to be, the models need to be rebuilt, etc. So still quite a bit of work here. I mean, we're just starting at this end now, but so far it looks like we shouldn't have an issue there. Okay, so finally we managed to achieve our goal of between 15 to 30% prediction accuracy with these stack ensemble algorithms. And management are excited as us now about credit scoring and what potentially we can do. Still quite a few models to migrate to this platform. We migrate away from SAS to SAS Via. But the plan is within the next year to basically migrate all our credit scorecards based on the results we've achieved. Yeah. We've also pretty excited because now we can start addressing the sort of unstructured data, alternative data, non-bureau type data space. SAS models we've used in the past were not really suitable for that. The inference cost issues are described using the teacher-student method. To overcome that, assists us quite a lot to keep the cost low. And as I said, still some work on the monitoring pipeline. So also quite delighted that we've got many reusable components. We're moving now on to time series demand forecasting. We're also going to use, go through a similar approach and use some of the cutting edge time series forecasting algorithms in that space in the fully automated workflows. And after our e-commerce recommendation engines is another problem area we're going to tackle. But they will follow a similar architecture, obviously different algorithms, but many of these architectural components that we have, we can reuse for those type of developments as well. Okay, that's it. Thank you very much.